Okay, so that's a few of the facilities we use to address this problem of the Hubble tension. The note is here, not the only one, but it's a very important one because first it has good seeing, second is our only telescope, well not ours, the only telescope of the collaboration in the north. And of course we are using or plan to use the LSST. Euclid will be a key ingredient in that project. We have time obtained on James Webb. That's the 2.2 meter at LSST that we use, the VST at Paranal, and the 1.2 meter telescope at LSST. You see behind the light curves, which is our main product in the end, this business of cracking the Hubble tension. And what is the Hubble tension? So people often ask us, so why are you after H naught to 1%? You don't need this. If you do astrophysics, you indeed don't need this. If you do cosmology, you need it. And one of the main problems cosmology has now is what we call the Hubble tension. So it's a tension between essentially two values of H naught. And that's the plot that summarizes everything. So if you want to study the universe, what you want to measure is H of Z, how H varies as a function of redshift, and that's predicted by a cosmological model from redshift 0 here to essentially infinity, but where you can observe, when you can measure an important value of the Hubble parameter is at redshift 1100 with Planck. So how you do this? You take the power spectrum of the CMB, you take the first peak that corresponds on an angular scale on the sky, but it also corresponds to a physical scale of the sound waves at that redshift. And then that gives you a distance by comparing the physical scale of the bionic acoustic oscillations at that redshift to their angular scale. Okay, that gives you H of 1100. Then if you extrapolate this down to redshift 0 with a cosmological model, that lambda CDM, for example, you end up here. And that's the value Planck measures in the absence of curvature. And that's around 67. Now, if you can also measure H naught in the local universe, many methods, supernovae, Cepheids, tip of the red giant branch, water masers, lensing, all this measures H naught directly in the local universe. If you do that, you find a different value, the Hubble constant. Now, problem is the Planck value wrong? Is the local measurement wrong? That means 5 or 6 different cosmological probes. Or is the curve wrong? Which is much more interesting, of course, because that means cosmology has a problem. So we want to know if, which of the three things is wrong. What lensing can do for you is to estimate an independent value of the Hubble constant in the local universe. And it's very nice because lensing is very nice because it's a single step method, no ladder, no calibration, no dust extinction, no nothing, but you still have kinematics, and I will show what they are. So first, what's the phenomenon? So if you have an observer, a source, and a lens, you see that arrival time of photons from the source to the observer will be different along different optical paths, and for two reasons. One is that the optical paths are different in length. Second, photons are delayed at different positions of the potential well of the lensing galaxy because of gravitational delay. So you guess already that the total delay of photons between image A and B of the quasar that you see here has two origins. One is geometrical and one is gravitational. Now, how does this work? So actually, that's the Norwegian guy who invented this effect. And essentially, the principle of the measurement is that time delay between two different images of your quasar or variable source, can be a supernova, depends on the lens redshift, the redshift of this one, the ratio of the three distances between you and the lens, you and the source, and between the lens and the source. And this is inversely proportional to H naught. Then you have angles, so essentially the geometry of your lens system, and that's the potential well of the lensing galaxy. And so the goal is you measure the time delay, the lens, the redshift of the lens, not an easy task, by the way. Then you get high-resolution images of your system, and you need the lens model because you need the potential well at the angular position of the lensed image on the plane of the sky. Now, if the universe is big, let's say, then the delay will be bigger than in a smaller universe, and H0 will be inversely proportional. So that's the whole summary of the effect. We've been doing different projects to measure these delays. Started with the COSMO-GRAIL project, cosmological monitoring of gravitational lenses, something I started back in 2004. Håkon was saying that you have to be patient to do the game. We are patient. At the same time, Sherry Soyuz started to do intensive lens modeling, and we joined forces to do the H0 lenses in COSMO-GRAIL Wellspring program, holy cow. So that's acronyms are acronyms, complicated ones. So actually, she's the one responsible for the crazy acronym here. Now we simplified, we call this time delay cosmography. So then our new joint collaboration is time delay cosmography. There is a website, an ERC project related to this. You can go and see this if you want. Principle of the method, what are the ingredients for this to work? So you need lenses, cover them. You need HST images because you need the detailed structure of the objects. You have here 1, 2, 3 images, 4 images of the same quasar lensed by a galaxy. And the ring you see there is the lensed host galaxy of the quasar. Now, it's not the only thing, so you need to measure the delay. I will come back to this. Once you have done that, you're not done. You need a detailed mass profile of the lensing galaxy at the position of the lens images. That's the lens model. And you're still not there yet. You need also to estimate how much of the mass of all the galaxies along the line of sight leak into what we call the Einstein ring of the lens. That contributes to the delay of photon. You need 3 ingredients: delays, lens model, line of sight, and companions to the lens. Now, for the delays, how do we do that? So, of course, we would dream to have HST and observe every night. We don't have that. That will be the type of image. That's an HST image, by the way, of the object I showed you before. That's what we get with a smaller telescope from the ground. So we use deconvolution photometry. So we deconvolve this and get that. So it's quite close to the image. The HST image has not been used for convolution. And then we separate the extended source from the point source, PSF, and we do this simultaneously for all the images, and that gets you light curves. So this as a function of time, the PSF changing. So that's not observations, but we do the same with the not observations. That's the lens quasar. Okay, so that's for how we do the photometry. Once you do the photometry, you obtain this kind of data. So now that's the same object. That's now the HST image. You see it, changing with time. Again, as Håkon said, you need to be patient to do this. But in fact, I will show you that you can go faster than a decade to observe delay. So actually, how you measure the delays, I didn't say, but you have a variable object. The variations will be seen delayed in time in the different lensed images. Okay, so that's the light curves you get with deconvolution. If you shift them by the delay, the curves match, but not quite. There is a difference between the different curves of the different images. You can model this with a linear trend per season, for example, or with a spline, and that fits better. You see that all the lens images have the same light curve modulo some differences. And that differences are due to microlensing. Oops. Sorry, one. Really need this. Sorry about that. Okay, so microlensing, what is it? So now this is a big zoom on the lensed image. This is now a few micro-arc seconds across. And these are microacoustics, so areas of the sky where the source, the accretion disk of the quasar, there, remember it's a super zoom, the area where the magnification by stars in the lensing galaxy are maximum. And then the quasar moves behind this, or the microlenses move in front of this, and that will create variations that are different, geometric variations that are different in each quasar image. And that's very slow. That can last several years. That's problematic when you cross-correlate your light curves, because you have to model this or potentially remove it. So what we do, that's another light curve of a quadruply image quasar. What we do is now instead of observing once per every few days or week, we observe every day to catch the fast variation of the quasar that are faster than the very slow microlensing variations that I was showing before. So if you do this, instead of observing here from 2004 to 2018, you zoom in some nice region. Actually, this is not a zoom, it's a simultaneous observation between a small telescope at low cadence and 2.2 meter at LSST at high cadence every day, and you immediately see that some details that you barely see here in these curves are now prominent bumps that can be used to measure very well the delay. And the microlensing variations there would last the whole season, while the quasar varies within 2 weeks. So that's how we do it now. So that's now, instead of years and years of observations, that's now one season here, 1 season here for each object. And we measure, so with the 2.2 at LSST, in 30 minutes per day, we have a precision of 3 millimag on the photometry. That's actually better than LSST per epoch, both in terms of signal to noise and in terms of sampling. That's the type of curve we get. So that's at the 2.2 meter. We also do this at parallel, where we have the same kind of exposures. That's an illustration of the other things you can do with the same data, because at parallel you have a 1 square degree field of view. You can discover quasars from the variability. You can discover supernovae even on day 0. You discover variable stars. You can discover lensed supernovae. We didn't for now, but we are closely monitoring this. And as a bonus, you even get space junk. So that's what you get when you do difference imaging between the big 1 square degree images. Every 5 minutes, you get this kind of sample of space junk. You see some of them are even spatially resolved. Some must be asteroids. Some are known stuff. So if someone wants the data to these kind of things, they are free to ask. Now, the NOT, it's a NOT conference, so that's our results. I think no one has seen these curves so far. So that's an object we observe at the NOT daily or almost daily. Again, 30 minutes of exposure. That's the deconvolution of the object. That's the HST image and light curve. So we have not finished that object, but it's clear that within a year we'll get very good delay. Another one, so that's a double. That's the HST image. That's the less impressive but useful NOT image that allows you to get these bumps. So you see the delay there. Now we are going to fainter objects. So curves may be less impressive than the previous ones. They're really useful. And the season is not over for this. And a very impressive one we have is this one. It has 6 images. In fact, it's the first case of a lensed binary quasar. So you have the lens galaxy here, and then you have 1, 2, 3, 4 images of one quasar. And then next to this quasar, there is another one, which is double image. One image is here, one image is here. What you see in the deconvolved. And that's the 4 light curves of the 4 brightest images. You see that, here that we'll get a delay of this. You see some gaps here. That's November. That's the volcano. But the object is circumpolar, so we can still observe it. Definitely we'll get a delay on that one. Even better, we'll get the second delay between this guy and this guy. So we get the delays between the 4 images plus the delay between the 2 images. And that's really a golden lens in many respects. Just to show you an example of the slow microlensing, now we take the difference, the light curve of the differences between A and B between A and C. So this is between A and C. So you subtract the two light curves, which means you remove the intrinsic variation of the quasar. That's flat. Now, if you have microlensing in one of the images, for example, in B, that's what you get. You remove what the curves share, the intrinsic variation of the quasar, but not the microlensing. That's what we are fighting with the high cadence observation. So that's a nice example. You know, it's not small variations. This is 0.7 magnitude 1 year. So this is the object now seen with HST. So I said it was a golden one in many respects. So it has, you know, the 4 images I was speaking about, these two. It has an Einstein ring. It has also a second source at a different redshift, this bluish thing. It is lensed by the same lensing galaxy, and that removes a lot of the lensing degeneracies we are fighting all the time. And on top of that, it has a proximate template alpha absorber in front of the binary quasar. So, you know, there is a lot of follow-up to do. We have time on the GTC to follow this up. So let's see how the observations will. Okay, just a quick view on that. Actually, you don't see the figure very well here, even not at all. It's for each system, the precision we have on the delay, depending on the length of the delay. So the color code is the length of the delay. The more you are close to the center, the more you are in the, let's say, what's the size? That's 5% precision on the delay. So that's where we stand. Almost all these delays are, in fact, from group, aside from our results. So for now, what we find is a high value of the Hubble constant, 7 well-analyzed lenses. Our target is 50 lenses. That's why we need to measure the delays. You know, delays are main ingredient in this study. If you want to know more about the latest results, go to these papers. So that's the total PDF we get for H0, for the 7 objects we have. We also check that we don't have a strong dependency on the lens model we adopt. In this case, we have a simple power law. Maybe you would say it's too simple. Then we go for a composite one, stars plus dark matter halo, and that's what we get. You know, no big difference. 74 here, 74.2. Essentially, it's almost independent of the modeling type. Now, if you go back to the Hubble tension, that's H0. This is what you get from the early universe, so Planck type of measurement, extrapolating back to redshift 0. And that's the different local measurement of H0, so shoes, supernovae, with 6 lenses, that's what you get. 7 lenses, that's what you get. Then since, you know, supernovae and lensing are completely different, so there is absolutely no correlation between what you get with supernovae and with lensing. You can combine. That's the result you would get. Now, if you trust this and trust this, then there is a 5.3 sigma tension between Planck value of H0, the local measurement. Future avenues, well, lot to do. So we have James Webb time now to only one lens actually, but with near spec to get the spatially resolved velocity dispersion of the lensing galaxy. If we do that, we can reach 4% precision on H0 with one single lens, meaning 1% in typically 10, 15 lenses. Actually, one negative point we had with this James Webb proposal is that we should have applied for, in fact, all the objects. We thought they would say the opposite. We would apply for all the objects. Okay, so anyway, this is in the queue. Second possibility is to, resolve kinematics is really important to improve further the lens modeling. Now, problem is unless you have James Webb or AO or something like this, it's very hard to do the resolve kinematics on an object that is completely outshined by the quasar images. But you can do a hierarchical Bayesian analysis of many lenses, some that have quasars, so you can measure the delays, and some that don't have quasars, but you can measure the velocity dispersion. Then, assumption, if all these lenses are from the same parent population. You can do hierarchical Bayesian analysis and inform the lenses with a time delay of the, let's say, mass profile of the lenses with no time delays, but with a velocity to join the strength of the different types of cells. So we have the two approaches. So James Webb will be used. This is being implemented as well. So Euclid will be very important in finding the lenses and in training the models. But then you still have to do the kinematics. And another thing we are now starting is try to find lens supernovae. So we tried in the VST data we have. The field of view is a bit small, but LSST will find such. There are advantages there. So advantages and drawback. The supernova disappear. So that means you need to measure the redshift immediately and confirm the type. You need to do the photometry to get the delays. But then the supernova disappears, and you can go and do your resolved kinematics galaxy without the bright supernova. Of course, you have to be on time to catch things right at the right. So yeah, three avenues: James Webb, lens supernovae, hierarchical analysis of lenses with time delays and no kinematics, combined with lenses with no time delays but resolved kinematics, like the SLAC sample. Okay, summary. So strong lenses really are an absolute distance indicator. So it has its drawbacks. Our main drawback is that, well, there are two main ones. Let's say we need the time delay precisely. Not is there to help. We need a very well-constrained lens model for the lens galaxy. There are different avenues like James Webb or this hierarchical analysis. And thanks to the high cadence monitoring, now we know that we can measure time delays in 1, maybe 2 seasons instead of a decade. That's really a game changer. But you need, of course, a bigger telescope and available all the time. And really, it's extremely hard to find this in the world. The north, I think the north is one of the very rare one. The south, essentially, you have the VST that will stop next year, next September. And you have the 2.2 meter Atlas IA, but also in a bad shape, maybe lasting very long. So our hope, and in fact we are close to this, is to have 50 time delays by September 2023, still find new targets. We have, for now, robust results with only 7 lenses, but there are many students and postdocs working on doing the modeling now of these 50. We have HST images for almost all of them. And our current result for now is H0 equals 73.7 plus minus. We are around 2.5%. By the way, in finding the lenses, so we also use the NOT. So this is not all, but half of this is from a NOT opticon program where we confirmed, so we took alpha spectra of all these lenses. We confirmed 85 new ones. It's not negligible, kind of 20% of the whole sample of. So that's also a very nice NOT contribution. I don't like to say NOT. Sorry. It's a good contribution. Okay, thank you.